In this video, we are going to discuss a few essential and fundamental concepts for Simscape modeling. Specifically, we will talk about how to describe Simscape component fundamentals, using the foundation library, creating multi-domain physical components, dividing components into subsystems, setting initial conditions for physical variables, and logging physical variables for visualization. This training will be applicable for both the combustion engine and electric teams, as it talks about important Simscape fundamentals. The core example is a multi-domain DC motor model that has both mechanical and electrical domain to understand the Simscape fundamental concepts. We would also like to acknowledge and thank the Virginia Tech Formula student team for providing us with data about their vehicle, motors, engines, and batteries for us to use in this training. As an example, let's build an electromechanical system. In this case, a DC motor that is powered by a battery pack. Here, we convert electrical energy to rotational mechanical energy. This serves as an example of a multi-domain Simscape model. We concentrated on the electrical domain first to build our battery model in our Simscape introduction video. In this example, we will build the mechanical part and then complete the full DC motor multi-domain system. In Simscape, an energy flow is defined by its variables. Each energy flow is associated with two variables, one across and one through. Usually, the product of these variables is the energy flow in watts. Across variables are measured using a sensor connected in parallel to an element, for example, electrical voltage. Through variables are measured using a sensor connected in series to an element, for example, current. Every domain is characterized by different conjugate variables. For example, mechanical rotational domain has angular velocity and torque as across and through variables, respectively. There are other domains as well with their respective across and through variables. These are listed here. In addition to these existing domains, Simscape lets you define your own domains. Refer to the documentation for more details on existing domains and how to define new domains using the Simscape language. Like with real physical components, you can branch physical connection lines. When you do so, the through and across variables obey Kirchhoff's laws. For each through variable, the sum of all its values flowing into a node equals the sum of all its values flowing out. For example, in this circuit here, I1 plus I2 plus I3 plus I4 equals 0. Across variables have the same values at directly connected conserving ports. For example, in this circuit, the voltage at the positive terminal of the resistor here equals the voltage at the negative terminal of the capacitor. Let's take a look at a couple of these examples. I'm going to switch to MATLAB for this. Let's open this model current law. We have a resistor network here consisting of R1, R2, R3, and R4 connected at this node here, powered by a DC voltage source. We are then placing current sensors in series to each of these resistors to measure the current here. Let's simulate this model and take a look at the current flowing through these resistors. We see that the sum of the currents at this node is 0. This means the model obeys the current law. Let's go back to MATLAB here and open up the other model voltage law. Here we have a two resistor network R1 and R2 powered by a DC voltage source again. We are measuring the voltage across the DC voltage source, R1, R2, and the ground here. Let's go ahead and simulate this model and take a look at these voltages. We see that the DC voltage plus the drops across the resistors equals 0. This means the model obeys voltage law. Similarly, any other Simscape model, whether it is an electrical system, mechanical system, or hydraulic system, it obeys Kirchhoff's laws for their respective through and across variables. Let's get back to the presentation here. We will start by modeling the mechanical part of the electromechanical system using the fundamentals we just discussed. This consists of a spinning inertia and a gear system. To model this component in Simscape, we will use several blocks from the Simscape foundational mechanical library. Let's switch to MATLAB here. The ssc_new command opens a new model and automatically inserts mandatory blocks like the solver configuration block and useful ones like the physical signal to Simlink converter. It also gives direct access to our foundation library here and any additional Simscape products you may have like SimMechanics or SimHydraulics. The foundation library consists of several ready-to-use physical components for every Simscape domain, as well as a complete library of blocks dedicated to physical signals. Available components include actuators, sensors, and various physical elements suitable to build multi-domain physical systems. Finally, the command also selects ODE23T as the simulation solver, which is one of the recommended solvers for physical modeling, and also sets the absolute tolerance of the solver at 1E-3, which is recommended for physical system simulations. To begin modeling the mechanical portion, let's start by modeling the spinning gear subject to two forces: an external torque that is assumed to be from the motor, and a damping torque. The external torque can be modeled by using an ideal torque source. Let's go ahead and access this by going to the Simulink library browser here. Scroll down to Simscape. Under Foundation Library and Mechanical, go to Mechanical Sources to find the ideal torque source here. Let's drag this block into our model. I'm going to rotate this block using the shortcut Ctrl-R. This is a variable source block in the sense that we can provide a physical signal as an input to convert to the required torque as input to our system. To specify this torque value, let's use a Simulink constant block. To do this, let's go back to our library browser, scroll up to Simulink, and then Sources, and drag a constant block into our system. Now let's go ahead and connect the constant block to the Simulink to physical signal converter block and convert the physical signal to our ideal torque source here. Double-click the Simulink to physical signal converter block to take a look at the unit specified here. It says that this is 1. This means Simscape will use a default unit for this signal. In this case, for the torque value here, the default unit will be Newton meter. Notice also that the Simulink to physical signal converter block has an input handling tab. This has options for filtering the Simulink signal before applying to the physical network. This is useful to smoothen very fast Simulink signals before applying to physical systems. Let's select OK to save changes. Next, for the damping torque, let's use a rotational damper from the mechanical library. For this, let's go back to the library browser again and scroll down to Simscape, Mechanical, and Rotational Elements to find our rotational damper here. Let's drag this block into our system. Double-click this block to set the damping coefficient. The default value is 0.001 Newton meter per radians per second. For this particular simulation, let's just leave it at that. Select OK to save changes. We also need a reference for the mechanical rotational domain we are working with. So let's drag one from the mechanical rotational library here. To model the spinning gear, let's also drag an inertia block from the mechanical rotational library. Finally, to model the gear, we can use a Gearbox Block from the mechanisms library. This can be accessed by going to Mechanical Library and Mechanisms and drag the Gearbox block here. For the Gearbox block, the torque at the output is going to be gear ratio times the torque at the input. We can set the gear ratio for this block by double-clicking on this block. So in order to have the torque at the output twice that of the input, let's change the gear ratio to 2 and say OK to save changes. Let's go ahead and make these connections here. So I'm going to maximize the model. Connect the ideal torque source to the gearbox block here. The output of the gearbox is connected to the inertia here. Connect the rotational damper to the inertia here on one side and a rotational reference to the other side. Also connect the rotational reference to the ideal torque source other port because the torque is going to be provided with respect to the reference here. Now let's measure the angular velocity on either side of the gearbox. We can do this using the rotational sensors. Let's go back to our Simulink library browser here, go to Mechanical and then Mechanical Sensors to find the ideal rotational motion sensor block. Let's go ahead and drag one of these blocks into our model. Angular velocity is an across variable. So let's connect the R port here to the output of the torque source and the C port to a rotational reference here. Let's copy this rotational reference by right-clicking on this block and dragging it. We can then rotate this block using our shortcut Control R, so I'm going to rotate it twice and go ahead and make the connection here. We will use the W port to measure the angular velocity here. The A port is used to measure the angular position. We are not going to be using that, so let's terminate it appropriately. To do this, go to the Simulink library browser again. Go to the Physical Signals library. Under that, go to Sinks to find the physical signal terminator block. Let's drag one into our model and make this connection here to terminate our angular position. To do the same measurement at the output, let's copy all these blocks using Ctrl C, which is the shortcut for copying, and then pasting it here using Ctrl V, which is another shortcut. To measure the angular velocity at the output of the gearbox, let's connect the R port to the output of the gearbox here. Next, note that our scope block has only one input signal. In order to measure two speeds, let's go ahead and double-click on the scope and access the parameters by clicking on the gear icon here and change the number of axes to 2 and select OK to save changes to get two input ports here. Let's go ahead and make a copy of this physical signal to Simulink converter here because we have a second signal coming in, and go ahead and make the connection to the scope here. Now connect the output angular velocity to the physical signal connection ports here. Note that the unit specified by the physical signal to Simulink converter block is 1, which means Simscape is going to use default units for the angular velocity measurement. In this case, it's going to be radians per second. Let's select OK to save changes. Let's go ahead and name our signals here. I'm going to call the first signal input speed and the second signal output speed. Finally, let's connect the solver configuration block to any part of the physical network to set the solver settings for our physical network here. Let's go ahead and simulate the model and take a look at our input and output speeds here. Hit the auto scale button to bring our signals into view. Here we can see that the input speed is twice that of the output speed because torque is multiplied by 2 on the output. Let's go back to the presentation to do a recap. We first used the ssc_new command to bring up a template Simscape model pre-populated with the necessary and useful Simscape blocks. We then used the foundation library to start building the mechanical system. A good way to think about Simscape networks is to visualize every connection point as having a consistent across variable and to visualize the blocks as applying the through variable. For the spinning gear, there exists a connection point that is connected to the inertia, external torque, and the damper. Then we use the gearbox block to specify the gear ratio. Note here that component polarity affects the usage of specific blocks like the gearbox block. Connecting the ports of this block to the correct components determines the appropriate gear ratios applied. For example, let us suppose the gear ratio of this block is 2. In this case, the output torque is expected to be twice that of the input torque. However, if we were to flip the connections between input and output for this block, the output torque would be half of that of the input torque. We have successfully modeled the mechanical part of this system. The next step is to combine our electrical and mechanical models to create a multi-domain system. We have the electrical battery system on the left and the mechanical gear system on the right. And we are going to interface these two using an electromechanical system, for example, a DC motor here. DC motor is an example for one of several different multi-domain blocks in Simscape. Some examples are shown here. Each of them contains multiple physical domains. Some examples are obvious. The hydraulic cylinder contains at least mechanical and hydraulic domains. Some are less obvious. The gear, rack, and pinion contains two physical domains. The rotating mechanical systems and translating mechanical systems are modeled using different across and through variables. The level of detail of your model will determine how many and which domains you will need to include. For example, the motor contains at least the rotational mechanical and electrical domains. However, if thermal effects are important to your system, you may need to include the thermal domain as well. Connecting physical systems requires setting up connections that properly capture the energy transfer between the different domains. In many cases, an ideal connection is a good starting point and may be sufficient for the final model. Simscape provides blocks for modeling ideal connections between the physical domains. For example, the lossless rotational electromechanical converter here. It is not always the case that connections between domains provide an ideal transfer of energy. Often, you may want to model energy losses in the system as you convert from one domain to another. For example, a DC motor here can model copper losses due to thermal effects. Let's switch to MATLAB to see how to build this multi-domain system. We already have our mechanical system here. To interface this with our electrical system, we need a multi-domain block. In this particular case, we could use a rotational mechanical converter to model lossless energy transfer. This can be found by going to the Simulink library browser, going to Simscape. Under Electrical and Electrical Elements, you can find the rotational electromechanical converter. Or we could use a DC motor, and this can be found in the Sim Electronics library under Actuators and Drivers and Rotational Actuators here. Let's use a DC motor and drag one into our model here. Let's go ahead and parameterize our DC motor. To do this, double-click on the block. There are several ways to parameterize the motor. You can do this either by using equivalent circuit parameters, by providing data about torque or no-load speed, or power and no-load speed. Let's use the equivalent circuit parameters here and provide the various values. The armature resistance for our case is going to be 0.0093 ohm. Our armature inductance is 172 microhenry. Note that the units are in Henry here. We could simply type U and capital H in order to make it microhenry. So this is a drop-down box as well as an edit box for you to specify other units that you do not see in this drop-down. Make sure that the units that you specify make sense for the quantity that you're specifying it for. Let's also specify a back EMF constant. In this case, it's going to be 0.19. This data was provided by the Virginia Tech Formula student team for their motor. Mechanical properties of the motor, such as inertia, can be accessed by the tab here. We have inertia, damping, and initial rotor speed as parameters here. For our model, we are going to keep this at our default values, so select OK to save changes. Notice that this model is beginning to take up more space. As you add more complexity to your models, you might find it useful to divide the model into functionally related components. You can do this by using subsystems. Subsystems can be created by grouping related blocks. For example, let's select the damper block here, the inertia, and the gearbox block. Right-click on the highlighted blocks and say Create Subsystem from Selection. Simulink automatically wraps all these components into a single subsystem. You can access the contents of the subsystem by double-clicking on the block to see our components here. The blocks here are called connection ports, which can help us interface this block with the rest of the system. Let's rename these blocks. The input to the gearbox is going to be shaft A. The output of the gearbox is going to be shaft B. And this is going to be our reference port. We can also choose the port locations. For example, A and reference need to be on the left-hand side of the subsystem. So let's go ahead and double-click on this block and make sure the port location on the parent subsystem is on the left. So for the reference, it's also on the left, which is good. We would want the output to be on the right, and this is specified to be on the right, which is good. So select OK to save changes. Now let's go back one level up by following this breadcrumb and clicking on the model here. And we can see that our port locations are correctly on the left and right, and the port names also have updated. Let's go ahead and rename the subsystem to be Gear Subsystem. We can do something similar for the sensors here. So let's select all the blocks with respect to our sensor system. Note that a pop-up menu here appears. We can also create subsystem by clicking on the first option here. Let's resize the subsystem and double-click on it to access the content underneath. Here, let's go ahead and rename our ports. So this is going to be A. This is going to be shaft B. These are our input and output speeds, so we can say I and O here. Let's go back one level up to see our sensor subsystem. Here we can go ahead and rename our subsystem. Let's call this sensor subsystem. Note that Simulink automatically creates appropriate physical ports and Simulink ports based on the signal types. For example, in the sensor subsystem here, these are physical connection ports and these are Simulink signal ports. Let's go back one level up. Now we have a cleaner model to work with. To complete the mechanical part of our system, let's go ahead and delete our ideal torque source here, because we are going to replace it with our DC motor. Let's go ahead and bring our DC motor here and connect the DC motor to our gear system here. Let's bring in our electrical battery system. I'm going to open a pre-built model for this. To do this, let's switch back to MATLAB and open up battery_subsystem. This model already has the battery pack as a subsystem. I can now explore this by double-clicking on the subsystem here. Here we can see there are 24 cells inside the battery pack, each of which is connected in series and is a subsystem by itself. Let's double-click on one of the cells and we can see that each one of them is an equivalent circuit model which we discussed in the Simscape introduction video. You can now imagine how big and messy our model would have been without using subsystems here. Let's go back to the top level of the model by clicking on the breadcrumb here. Let's copy this block into our system. So I'm going to select this block and use the shortcut Ctrl+C. Go back to our other model and press Ctrl V to paste this block into our model. Now let's connect the battery pack to the DC motor here. So connect the positive port of the battery pack to the positive port of the DC motor, and similarly the negative port is connected as well. Before we simulate the model, let's go ahead and rearrange these blocks to make this model cleaner. So I'm going to resize the scope block here. Now let's go ahead and simulate the model and take a look at the output. We see an initialization error here. The error says tie this variable to a definite value by connecting a domain reference block. We've talked about this before. Each domain must have its own reference. The mechanical part has this domain reference here. However, the electrical part does not have a domain reference. So let's insert an electrical reference block here. To do this, go to the Simlink library browser again, scroll up to Simscape, and under electrical library, go to electrical elements to drag in our electrical reference block from here. Let's go ahead and connect this to our negative port of the battery here. Let's go ahead and simulate the model again and take a look at our scope here. Here again we see that the input speed is twice that of the output speed, and that is because the gear ratio is 2, which multiplies the torque on the output. Let's go back to the presentation. We just saw how to make subsystems to make the model easier to read, navigate, and reuse components. This also helps us organize our model in functional blocks. We also saw that the data transfer across subsystem borders can be done through input and output ports, which are Simulink signals, and connection ports, which are Simscape connections. Many Simscape components contain internal states with initial conditions. For example, the initial velocity of the gears can have impact on the simulation results. Before the start of the simulation, the solver automatically determines initial conditions for all internal states in the physical network. If it fails to find a consistent set of initial conditions, you will receive an error message. We can provide the initial conditions to physical variables in a Simscape model. Let's go back to MATLAB to see how we can do this. In our model, let's assume that we would like to specify the velocity initial condition of our inertia in the gear subsystem here. To guide the initialization process for a physical variable, double-click on the corresponding Simscape block, in this case our inertia block, and access the Variables tab here. For each variable initial condition you would like to specify, enable the checkbox Specify column. Then provide the required initial condition value. In this case, I'm going to say it is 10, and the units are going to be in radians per second, so I'm just going to leave it at that. Set the priority value to high. If there is a conflict between initial conditions for different priorities, Simscape will make sure the high priority target is met first. Select OK to save changes. In our model, the inertia here and the DC motor here have their velocities dependent on each other due to the motion constraints set by the gearbox underneath the gear subsystem. Let's see this in action by setting the initial rotor speed for the DC motor as well. To do this, double-click on the DC motor, go to the Mechanical tab, and set the initial rotor speed to 10, and remember to change the units to radians per second. Select OK to save changes. To view the initialization, go to Analysis, Simscape, and then Variable Viewer. This window shows all the physical variables in our system and their initial conditions. I'm going to collapse all these variables here. Let's go ahead and take a look at the DC motor's initial rotor speed here by selecting the inertia block. We see that the initial condition that Simscape has come up with is 12. Similarly, let's take a look at the initial condition for the inertia here. We see that the initial condition is 6. Notice that both the DC motor and the inertia's target is set to 10. But because of the gearbox, there is no way this is a physical condition that can be achieved. To avoid initialization conflicts like this, we recommend assigning a high priority to only one of these initial velocities. The other components can be guided with low priority targets. So let's go to this inertia's block dialog by right-clicking on this inertia and saying Open Block Dialog. Go to the variables and select priority to low and select OK to save changes. And let's rerun the initialization by refreshing the viewer here. I'm going to collapse all the variables. Let's take a look at the DC motor's initial rotor speed and the inertia under the gear subsystem here. You can see that all the high priorities are satisfied, but low priorities are not satisfied. This is what we expected. Now the DC motor's initial rotor speed is set to 10, and the inertia's initial angular velocity is set to 5. This makes sense given that we have a gear ratio of 2. Let's go back to our model here. Next, you might want to log simulation data to the workspace for debugging and verification. By default, simulation data is not logged. To enable data logging for a model, open Model Configuration Parameters here by clicking on the gear icon. Go to the Simscape section. Make sure that the Log Simulation Data option is set to All. And select Limit Data Points. And select Apply. Now, when you simulate the model, Simscape will automatically create a workspace variable named Simlog, which contains the simulation data. Let's go ahead and see this. Select OK to save changes and simulate the model here. Let's go back to MATLAB. Now we see here that there's a variable called Simlog. In order to explore this, we can type the command ssc explore and then provide our variable here Simlog and execute the command to open up the Simscape Results Explorer. This shows the various internal variables of the block. For example, under the gear subsystem and the rotational damper, we see the angular velocity of the rotational damper here. You could also open up this Explorer automatically after every simulation. To do this, go back to the model here, go to the Model Configuration Parameters again, and under Data Logging Options, you could say Open Viewer after simulation to automatically open the viewer once the simulation has terminated. The other big motivation to log simulation data like this is that it doesn't take up as much space as a sensor subsystem like this here, which uses a sensor block, a converter block, and a scope block. Let's go back to our presentation here. We talked about setting initial conditions for physical variables. These can be accessed in the Variables tab of a Simscape block dialog. To avoid initialization conflicts, we recommended assigning a high priority to only one of these initial velocities. We tested this using an example and used the Simscape variable viewer to see how constraints in the model made initialization fail. We then relaxed one of these constraints to lower priority and saw that Simscape solved for the higher priority variable while not satisfying the lower priority one. Finally, we also saw how to log variables using the Simscape Results Explorer. If you log simulation data to the workspace, you can later query, plot, and analyze it without rerunning the simulation. Data logging can also replace sensor, converter, and visualization blocks, which increase the model complexity and slow down simulation. In summary, we talked about essential Simscape fundamentals, for example, variables, polarity, and so forth. We used the Simscape Foundation library to build a system and talked about building subsystems to maintain a cleaner model hierarchy. We then talked about creating multi-domain systems using our DC motor as an example. Finally, we talked about setting initial conditions for simulations and logging physical variables. This concludes this video.